Hello student, I am Arnab. Today we again meet together for continuing our last day class, that is the amplifier for a transistor. Today we discuss about the amplifier on the basis of the mode of operation. For small signal amplifier, the main factor are usually amplification, linearity and magnitude of the gain. But if you consider for a large signal or the power amplifier, that time primary motto is that you should design that kind of amplifier where the sufficient power can be delivered to the output load or driver. It may be a speaker or the power device. And for that case, their power output can be few watts to up to 10 watts. The main feature of a large signal amplifier are circuit power efficiency, the maximum amount of power that the circuit is capable of handling and impedance matching to the output device. So, amplifier classes represent the amount of input signal varies over one cycle of operation for a full cycle of input signal. If you just follow this waveform, that time it will be able to easy for understanding. How much portion is amplified on that point of view or mode of operation on that point of view, amplified power amplifier basically classified into some pattern or name, that is the class A type of amplifier. This is the first one where the output signal varies for a full 360 degree of input signal. You just concentrate your mind in this point, that is the full 360 degree of the input signal will become as the output side also, and that time the bias or Q point you should be put it at the half position of the supply. Now for the class B type of amplifier where the output signal varies over the one half of the input signal or cycle or for 180 degree of the signal, and that time the bias at the zero level position. For the class AB type of amplifier, the amplifier may be biased at a DC level above the zero bias circuit level of the class B and above one half of the supply voltage level of the class A. So that means for the class A and the class B, this is the combined form will be represent the class AB type of amplifier. For the class C amplifier, the output of a class C amplifier is burst for a operation at the less than 180 degree of the cycle and with operate only with a tuned circuit which provides a few cycle of operation for the tuned or resonant frequency. And for a class D type of amplifier, what happened? The the operating class is a form of amplifier operation using pulse signal which are on the short interval and off for a longer interval. Now we discuss about the power efficiency. It will record for the analysis of the power amplifier also. If you look on the table, that time it can be easy for understanding that what kind of power efficiency will be varies for the power amplifier if you consider for the class A, class A, B, B or various one. If you check on there, the operating cycle is 360 degree for the class A. For AB is in between 180 and 360 degree. For class B, it is 180 degree, and for the class A, it is less than 180 degree. For the D, there an pulse is provided on there. And what happened for the power efficiency? For the power efficiency, if you consider for the class A, that time the efficiency will be 25 to up to 50%. For the class AB, it varies from the 25 to 78.5%, and for the B, it is 78.5%. For the C, it is not considerable because here the efficiency is not given due to the reason of that the delivering large amount of power um, is not basically used for the class C type of amplifier. Now for the D1, they're typically over 90% for the power efficiency. Today we broadly discuss about the class A amplifier where the series feed class A power amplifier is used on there. Again, I just repeat that you already see that for the class A amplifier, their power efficiency in between 25 to 50%. So if you vary the biasing configuration, that time their efficiency can be modified and it may vary from the 25 to 50%. Initially, we just considered here the bias for the series one where the RB and RC is connected with the VCC and their configuration is look in this way. Look that RB and RC both are connected with the VCC. So for the fixed bias condition we are considering in here, if you check carefully on there, that time their current through the RB or base current will be defined as a VCC minus of 0.7 volt by of R of B. Why this is? You just apply the KVL in this path. That time what happened? VCC is equal to IB RB into V of C will be. So here, if you put the value only for the IB, that time the equation will become as VCC minus of VCE uh, by of R of B, and we know that for uh, transistor, if it is the silicon one, that time it will be 0.7 for the V of C. So you just put the value and that time the equation for the I will become as VCC minus of 0.7 volt by of R of V. And another one kind of equation can be write down on there, that is IC is equal to beta into of IB, because beta is defined the current amplification factor, and due to the reason of this is a C configuration. That time the output by input ratio for the current, output current is IC and input current is IB on there. So this is IC by of IB is defined the beta one. So obviously the value for the IC will become as a IC beta by of beta into of I of B. Now same way for the V of C, if you consider for the V of CE, so this is VCC minus of ICRB. You just look a careful notation that VCC will be maximum one when VCC will be maximum on that time when VCC will be maximum when IC will be 0 on there. When IC is equal to 0, that time their VCE is equal to VCC minus of 0. That time it will be the maximum value for this one. If you check on there for the characteristic curve, their DC load line is this one, and this is the AC or characteristic curve for the transistor one. So where it is skirted with the DC load line, that one is defined the Q point. If you want to consider for the class A type of amplifier, that time should be the Q point will be put at the middle of that one. That is the DC load line at the middle position. You should be use the Q point on there. And the what will be the maximum value on there? This is the VCC. Already you can identify by this one, because when the IC is equal to 0, that time VC will be as a VCC. And from this equation also you can write down IC is equal to VCC by of RC minus of VC by of RC. So if IC want to be maximum value, that time VC should be equal to 0, and that time the value will be IC as a VCC of RC. Okay, so for this reason it is defined the maximum value point for the IC is V of CC by of IC, and here the maximum VC is defined as a V of CC. If you connect between them, that time the DC load line will be created on there. So here if you apply the input one, that time what happened? if you apply the input signal on there, that time you just plot a vertical line for each and every point position, and then the same distance you just cover on there. That time you got it, the output section, that is the IC, what will be value, you can able to understand. So you have to consider for calculating the efficiency one, and for that cases the power drawn from the supply is, that is defined as a PIDC, will be defined as a VCC into of I into ICQ. Output power will be defined as a P0 AC, because here the AC signal is coming as output, and that time you should be considered the RMS value. V of C RMS we multiplied with the IC into RMS. Why? Because power is equal to V into of I. So if you multiply this to that time, there the power calculation can become for the output side. If you represent this into the form of the current, that time it will be represent for the P0 AC is equal to IC squared RMS pi of RC. Same way, if you consider into the form of the VC, that is the collector side voltage, that time the VC square RMS pi of RC. So any one equation can be useful for calculating the value for the efficiency one, because efficiency is defined as a P0 AC by of P of IAC, where P0 AC is defined the output power and in the form of AC, and this is P of IAC is defined the supplied power drawn. And if you multiply it with the 100, that time the efficiency will become as a percentile form. So maximum efficiency for this kind of biasing configuration, that is for the fixed bias, that time the maximum V of C already you can able to identify in here. This is V of E is VCC. So you just put this value as a position of the Vmax, Vc, this one. So same way, V's maximum value of the current is VCC by of RC. So you can also check this one in this position, where the maximum current is defined the VCC by of RC on there, and that time the maximum P0 AC will be defined the RMS value of the VC with multiplied with the current. That means anyone can use the equation on there, this one or this one, anyone, or this one also. If you put the value on there and you represent it, the RMS into the form, that time the value will become as a VC square by of 8 of RC. If here you consider for the voltage form, that time the power, the output side will become, this is VC square by of 8 RC. Same way, if you identify the value of input side, that is the supplied power for the DC one, it will become as a VCC into of ICQ, and ICQ is defined the VCC by of RC, and this is the RMS value, and for this reason it is defined as a VCC into a VCC RC by of 2. That means this is VCC square by of 2 RC will become as a input supplied voltage. And if you ratio between them, that is this one is here and this one, you just apply this position, that time the calculated value will become as a 25%. So this 25% can be modified up to the 50% if the biasing configuration is changed, and it can become as a 50% for the transformer coupled amplifier. So till now this is today's class, and hope you can able to understand, and we meet together again for the next day. Thank you.